Hi, this is Ms. Fitzmaurice, and this video is an explanation of the problem on page 34, which is the second, third, and fourth problem. They're not numbered, but it's pretty obvious there are four different sets of text on the page, so I'm looking at the second, third, and fourth. Okay, so before you watch this video, make sure you've spent 10 minutes trying to answer this question, and then come back and see the video. Okay, in number 2 it asks, at what distance from the center of the Earth should a satellite be placed so that it will have a geosynchronous orbit? Okay, so it's asking about distance, and we know that there's this satellite, it's going around the Earth, and if it's geosynchronous, that means as the Earth spins, the satellite goes with it. Okay, so the geosynchronous part tells us that the period of our satellite is equal to 1 day. Okay, and if we wanted 1 day in seconds, because remember we want all of our units to be in seconds, kilograms, and meters, so we take 1 day times 24 hours per day times 60 minutes per hour times 60 seconds per minute. And this is kind of what you did in chemistry forever. We can cancel out the days, we can cancel out the hours, we can cancel out the minutes, and we are just left with seconds. Okay, and when we multiply all of this through, we find that 1 day is equal to 86,400 seconds. Okay, so that's our period. At the end, it's asking us to find R. Okay, it says how far from the center of the Earth. So that's asking us to find the variable R. Now, there are a bunch of different tools that we can use. Okay, we can use our net force equation. And when you come across a problem like this, sometimes it's helpful to just brainstorm. What could I use? I could use F net equals MA whatever. Okay, it looks like it's not moving up and down, so I'm just going to say MAX. I can use the fact that it's moving around in a circle and say that my A is equal to VT squared over R. Okay, so that, again, that looks promising because I want an R. Okay, I know that the force pulling inwards on this satellite is the universal gravitational force. Okay, but it's not on the Earth's surface, so I can't use Fg equals mg. I'm going to use Fg is equal to capital G, little m for our satellite, the mass of the Earth divided by r squared. Okay, so that's pretty much what I'm going to use. The last thing I'm going to use is that my Vt is equal to 2 pi r over t. Okay, so let's look at these equations. You may be able to solve this much faster, but we can find the net force, okay? The Fg is going to go into my net force. If I look at the net force equation, I can check off what variables I know. Okay, G is always the same thing. It's 6.67 times 10 to the minus 11th. The satellite's mass, I don't know. The mass of the Earth, I do know. Okay, the radius, that's what I'm looking for. Okay, also in my net force equation, I don't know the mass, but I'm hoping that it'll cancel out. Okay, I don't know Vt, but you can bet that you're going to take this equation, 2 pi r over t, where the only thing you don't know is r, and you're going to put that into acceleration. Okay, so keep that all in mind. I'm going to go to the next page and try to plug things in. Alright, so I have sigma fx equals max. The only force acting is the gravitational force, so I'm going to write G capital M of the Earth, little m, divided by r squared is equal to little m. Okay, that's the mass of my satellite times Vt squared over r. Okay, and you notice right away I have an m right here, I have an m right here, so I can cancel those out. So it turns out this doesn't matter, or this is not dependent on the size of the satellite. Okay, again, I know that Vt is equal to 2 pi r over t, so I'm going to take this and substitute it in for Vt. Okay, and this might seem like a lot of variables, but I want you to try to do this all in terms of variables. Okay, so if you didn't get this far, I want you to take a minute, substitute this in for Vt, and try to solve for r, and then check back. Alright, so now that you've gone ahead and done that, we have Vt squared, so that's 2 pi r over t squared, all divided by r. Okay, I'm going to write that out, so I have G me, and before I do, I'm going to notice that I have two r's on the bottom, not inside of my squared, and that this will cancel out with this one. So I have Gme over r is equal to 4 pi squared r squared divided by t. Okay, I want to get all the r's by themselves. Okay, so I'm going to multiply both sides by r. Okay, and I'm going to end up with Gme is equal to 4 pi squared r cubed divided by t. Okay, now I want to get rid of everything that's not an r on this side of the equation, so I want r cubed by itself. Okay, so I'm going to multiply by t on both sides, and I'm going to be dividing by 4 pi squared. Divided by 4 pi squared. Okay, so now 4 pi squareds will cancel out, the t's will cancel out, and I have r cubed equals G, the mass of the Earth, times t divided by 4 pi squared. Okay, and then to get rid of a cubed, I can raise everything to the 1/3 power. So I'm going to raise both sides to the 1/3 power. Okay, or this is really taking the cube root, and I have r is equal to Gme, oops, sorry, that's the mass of the Earth, so Gme t over 4 pi squared to the 1/3. Now I can plug in numbers, so I know that G is 6.67 times 10 to the minus 11. I know that the mass of the Earth And actually, I'm going to rewrite this so there's more space. So the mass of the Earth is 6 times 10 to the 24 kilograms. And we found that our time was 86,400 seconds. Okay, and we're going to be dividing by 4 pi squared. Okay, if you have a graphing calculator, you can do this all in one step. If you don't, what I recommend is that you take all of the exponents out, okay, and you're just going to multiply 6.67 times 6 times 8400, divide by 4 pi squared, okay, then multiply that number by 10 to the minus 11th, multiply it by 10 to the 24th, okay, and then take the cube root. But if you do it all in one step on a graphing calculator, you should get the radius is 9.57 times 10 to the 5th meters. Alright, so the second question, or number 3 on the page, says at what distance, so it's asking for r again, will the satellite have a period of rotation twice as large around the Earth? So what you may realize is that nothing is changing in this situation except for RT, which is 86,400. So give me a second. 86,400 times 2 now. 6,400 times 2, because it's twice as many seconds. Okay, so we can actually use the final equation that we found. We can use the cubic root of g m e t over 4 pi squared to the 1/3, except we're going to plug in a different t, because the mass of the Earth is staying the same, g stays the same, 4 stays the same, and pi stays the same. Okay, so we have our radius is equal to the cubic root of g m e t over 4 pi squared to the 1/3. Okay, and at this point we're just plugging in numbers. So we have 6.67 times 10 to the minus 11. Okay, again we have 6 times 10 to the 24 kilograms, and the period is now going to be 86,400 times 2 divided by 4 pi squared, and all of this is to the 1/3 power. I shouldn't have written 1/2. And so all you have to do is plug that into your calculator, and when you do that, you should get a radius of 1.2 times 10 to the 6th meters. Alright, in number 4 it asks us how fast would a satellite have to go to orbit the Earth 200,000 kilometers. So that's telling us our radius, but notice it's telling us in kilometers. So it's 200,000, and then we know that 1 kilometer is equal to 1,000 meters. So all I have to do is multiply by 1,000, or add 3 more zeros. So it's actually 200 million meters from the center of the Earth. Okay, so we can start basically the same way. We're going to start with this idea that sigma fx equals max, but we're going to quickly replace that by the force, the universal gravitation force. Okay, and this capital M is for the mass of the Earth again, and the little m is for the mass of the satellite, divided by r squared, equals m, and then again, we're replacing a with vt squared divided by r. Okay, but this time we don't necessarily, at least for the first part, which is how fast, we don't care about period, we care about velocity. Okay, so keeping with what we've been doing so far, I'm going to first solve for vt. Okay, so I have this equation. I want you to take a minute, if you didn't get this far, and solve for vt. Okay, so I'm going to solve for vt for you. We canceled out our m's, the little m, importantly, not the big M, and we can cancel out this r with this squared. Okay, so now we have vt squared is equal to g me over r. I am going to take the square root of both sides, and I end up with vt is equal to the square root of g me divided by r. Okay, these are numbers that I can just look up. So I have g, which is 6.67 times 10 to the negative 11th. me is still 6 times 10 to the 24th. Okay, and the radius that they tell us here is 200 million. Okay, so I can just plug those numbers into my calculator, and when I do that, I get 1.41 times 10 to the third meters per second. Okay, to put this into perspective, that's like 1,400 meters per second, or more than a kilometer in 1 second, almost a mile per second, which is crazily fast. Okay, so that was my first answer. The other thing it wanted to know is what the period would be. Okay, so I can use vt equals 2 pi r over t. Okay, this is fairly easy to solve for t, so we're just cross-multiplying these guys, and I get t equals 2 pi r over vt. Okay, I know that my radius is 200 million meters, so that's 200,000,000. I could write this in scientific notation, and notice that it would be 2 times 10 to the 8th, because there are 8 zeros, or I would have to move this imaginary decimal over 8 times. Okay, divided by 1.41 times 10 to the third. And when I do that, I get 8.9 times 10 to the 5th seconds. Alright, so I hope that this has been helpful. One thing that I want you to get out of this, because we're dealing with such big numbers and so many exponents, is that you should pretty much always, and you should get in the habit of doing this in other physics topics as well, but especially here where we have really big numbers, make sure you always solve for your variable first, and then only when you have the answer in variable form should you start to plug in numbers. Otherwise, it will get very messy very quickly. So here we solved for vt first. Here we solved for t first. In the previous problem, we solved for the radius in terms of variables. Okay, so I hope this is helpful, and I will see you on Monday.